Hi and welcome to Maths class. In the previous video we looked at the antiderivative of ax plus b to the power of r for the case when r does not equal -1. So now we're going to look at case 2 when r equals -1. So I'm just going to take that away to leave more room on my page. So we're looking at case 2. So let's just go backwards a little bit. We're going to go back and revise some more derivative work. If I make capital F of x equal to the function log base e of x, and remember that the argument of a logarithm needs to be positive, so x has to be greater than 0, then I know that f dash of x is going to equal 1 on x. That's a derivative that we learnt, that we've previously learned. So that means that it must be the case that the antiderivative of 1 on x equals log base e of x, with my plus c, of course. So the antiderivative of 1 on x dx is going to equal log base e of x plus c. But there's a problem with that. This derivative here is only for x is positive, okay? Because my original function is only defined for x is positive. So I'm just going to show you how that looks on a graph. Now I've got two graphs there. The blue graph is my logarithmic function, f of x equals log base e of x. And the red graph is half of a hyperbola. It's only quadrant 1. So f dash of x is equal to 1 on x. And that's fine. But what I'm looking for here is not the derivative of a logarithmic function, but the antiderivative of the hyperbola. So here's the whole hyperbola. So I need to find the antiderivative also of the part of the hyperbola that's in quadrant 3. The hyperbola is symmetrical. So the easiest way to think about this is if I took my blue logarithmic graph and I reflected it in the y-axis, so that would be log base e of -x, then that would give me this. So I've now got a green graph, which is log base e of -x. So it's the blue graph reflected in the y-axis. And that graph has a negative derivative throughout, and the red part of my hyperbola that's in quadrant 3 is the derivative of that function. So that makes the antiderivative of a hyperbola kind of tricky because there are it's a piecewise function basically. There are two parts to it. It's going to equal the blue graph when x is positive, and it's going to equal the green graph when x is negative. And of course when x is 0, the hyperbola is not defined, so the derivative is not defined. So let's go back to our notes and have a look at how that will look. What I'm going to have then is, let's make this into a piecewise function, and this is going to be true for x is positive, and it's going to be log base e of -x when x is negative. And of course we're not going to forget our plus c's. So what I've found is that the antiderivative of 1 on x is actually a piecewise function, and it's going to equal log base e of x plus c when x is positive, and log base e of -x plus c when x is negative. But of course, we didn't start out looking for the antiderivative of 1 on x. What we're looking for is the antiderivative of this function, but when r equals -1. So in other words, what we're really looking for is the antiderivative of this function ax plus b dx. So when ax plus b is to the power of -1, we end up with 1 over ax plus b. So this is x to the power of -1. What we're looking for is this new function. So let's do that now. So now let's recall what happens if I have capital F of x equals log base e of ax plus b, which is what we've got here. And again, remember that the argument of the logarithm must be positive. So ax plus b is positive, which means we've got a is greater than negative b over a. So negative b over a, if I was to sketch this graph, would be my vertical asymptote. So that means if I find the derivative, what I did here was I found the derivative of the inside function, and that's a, and then the derivative of the outside function would be 1 on x, so that becomes 1 over ax plus b. So we did a lot of these where we found that if I had a linear function was the argument of a logarithm, then the derivative is a over ax plus b. So that means the antiderivative of a over ax plus b dx is equal to log base e of ax plus b plus c. In other words, it equals this, and I remember my plus c. But this is only true when x is greater than negative b over a. We've got to remember that. But I'm not looking for this. If you recall, what I'm looking for is 1 over ax plus b. Well, the only difference is the factor of a on the numerator. So if I write 1 over ax plus b dx, then that's going to equal 1 over a times log base e of ax plus b plus c, but again, remembering this restriction on my domain. So how do I know exactly what happens when I have x is less than this value? So the best way to, because this will be, of course, also an asymptote of this graph here, because ax plus b cannot equal 0, because it's a denominator. So what I want to do is just to remind you that if I actually look for the derivative, what if I had at the start f of x equals log base e of negative ax minus b? What would that give me? Well, using the same rule that I used before, f dash of x is going to be negative a over the original linear equation on the inside, negative ax minus b, which is going to give me a over ax plus b. So I'm going to get the same derivative here as I got for when I didn't have the negative signs inside the argument. So once again, I've got a piecewise function that's going to give me the two parts of the antiderivative of this. So that leads us to this general rule. The antiderivative of 1 over ax plus b dx is going to be 1 over a, so this is a piecewise function, 1 over a times log base e of ax plus b for ax plus b is greater than 0, or you can write x is greater than negative b over a, and it's going to equal 1 over a of log base e of negative ax minus b, so that's a reflection once again in the y-axis, for ax plus b is less than 0. So that's the two parts to our piecewise function. Now, there is another way to write this function, and that is 1 over a times log base e of the exact value of ax plus b plus c. Now, this is not part of the course, but this symbol, when we put the straight lines on the outside, mean we take the size of this and not the sign, which means that this and this together make up this function. So it's a shorthand way of writing it rather than writing both the parts out, but it's really important to remember that we're not going to just use half of the function. We need both sides of this function. So let's do a worked example. So the example I'm going to look at is find the general antiderivative of 5 over 2x plus 3. So this is the same as 5 times 2x plus 3 raised to the power of negative 1. This is the specific case where r equals negative 1. So I don't have enough room again on that page there, so I'm going to do it on a separate page, and I've rewritten the question to find the general antiderivative of 5 over 2x plus 3 dx. and I'm going to use the rule that I've just used, and I'm going to write it as a piecewise function. So I'm going to have two parts to my function. The first one is going to be the 1 over a, and if you remember this is ax plus b, then the 1 over a is going to be 1 over 2, and that's going to be the same in each part. I also need to keep this constant, so it's going to be also multiplied by 5 because that's the constant that was here. And then what I need to do is I have the logarithm, base e, for both parts, of 2x plus 3 up here, and negative 2x minus 3 down here. And then I just want to remember my plus c each time. And then I'm going to write in the domain. So I'm going to write 2x plus 3 is greater than 0, and 2x plus 3 is less than 0. And that's my solution. Oh, I should rewrite it because I really should collect these together. So let's just rewrite our final answer. 5 over 2 in each one, log base e of 2x plus 3, and log base e of negative 2x minus 3, and then 2x plus 3 greater than 0, 2x plus 3 less than 0. And I'm done.